Okay, guys, let's look at number 10 and 11 together since those two kind of follow each other. So we want to know what is the pH of a 0.01 molar weak acid with a Ka of 4.95 times 10 to the negative 10th. So a couple of things. First off, this is a weak acid. So that means that dissociation is not 100%. And so we are going to need to use the Ka expression. So we can't just use the 0.01 molar of our weak acid. So the first thing that I would do is set up a Ka expression. I also noticed that my Ka value is really, really small. 4.95 times 10 to the negative 10th is probably one of the weakest acids that we've seen. So remember, the smaller the Ka, the weaker the acid. But that also means that its conjugate base is going to be stronger. So knowing that relationship is really important. It doesn't give me a specific acid here, so I'm just going to use our generic acid, which is our HA. So we've got Ka is equal to the hydronium ion times the conjugate base, and then it's divided by our acid concentration. So we know the Ka value. We also know that our hydronium and our conjugate base, we're going to assume this is a one-to-one reaction. If it doesn't say otherwise, we can assume that, are going to be the same because those are our products. So when we make one of the product, we'll get the other product. This is kind of our x squared factor. And then we're going to divide it by the concentration of our weak acid. So with a little bit of rearranging, we realize that x squared is 4.95 times 10 to the negative 12th. And then x is 2.22 times 10 to the negative 6th. And that is molar. That's the concentration of our hydronium ion. Once we have the concentration of our hydronium ion, it's just a simple plug it into your pH equation, negative log of that value. We end up with a pH of 5.65. It's an acid, so I would assume that it's going to be under 7. But we also said with that 4.95 times 10 to the negative 10th value, it's a super weak acid. So 5.65 makes sense to me. Now, number 11 asks, what's the Kb of the acid above? So we need to know the relationship between Ka and Kb. So Ka times Kb is equal to the Kw. So we know that Kw is a constant for water. It's that dissociation constant. And so as Ka goes up, Kb would go down. In our case, Ka is really, really small. So I'm going to expect a higher Kb value. So Ka was given in the last problem, 4.95 times 10 to the negative 10th. Kw is a constant value. It is on your gold sheet, so you don't need to memorize that one. 1 times 10 to the negative 14th. And then Kb is our unknown. So when we do a little bit of rearranging and plug our values in, x or Kb is equal to the Kw, 1 times 10 to the negative 14th, divided by our Ka, 4.95 times 10 to the negative 10th. Our math, that gives us a Kb value of 2.02 times 10 to the negative 5th, which is kind of twice what the value of our Ka is. It's much larger, and so that would be what I would expect in a problem like this.